Let's now go ahead and take a look at example 5. In example 5, we're asked to find the Laplace transforms of the following two functions. However, we don't need to kind of reinvent the wheel on these and go back and solve them from scratch using the definition of the Laplace transform. What we can actually do is use some of the previous results that we just found, along with the fact that the linearity of the Laplace transform. So remember, because the Laplace transform is linear, if you have a linear combination, let's suppose it's c1 f of t plus c2 g of t, the Laplace transform of that linear combination is simply going to be c1 times the Laplace transform of f plus c2 times the Laplace transform of g. Because of that, if we take a look at example 5 part A, we're asked to find the Laplace transform of 1 plus 5t. Due to linearity, this is simply going to be equal to the Laplace transform of 1 plus 5 times the Laplace transform of t. And now each one of these was one that we had done earlier. Recall that the Laplace transform of 1, that was equal to 1 over s, and recall that the Laplace transform of t was 1 over s squared. Therefore, this Laplace transform is going to be 1 over s plus 5 times 1 over s squared. You can write as 5 over s squared. And for both of those Laplace transforms to exist individually, recall that that's going to be valid for s greater than 0. Similarly, we can use linearity on the next one. This is going to be 4 times the Laplace transform of e to the negative 3t minus 10 times the Laplace transform of the sine of 2t. We had found earlier that the Laplace transform of e to the negative 3t, that was going to be 1 over s plus 3 for this piece. And we saw that the Laplace transform of the sine of 2t was 2 over s squared plus 4. So this is going to be 4 times 1 over s plus 3 minus 10 times 2 over s squared plus 4, which we can rewrite as 4 over s plus 3 minus 20 over s squared plus 4. Let's talk briefly about where these are going to be defined. If you go back to the first Laplace transform, this was actually valid for s greater than negative 3. For the Laplace transform of this overall thing to be defined, both of these have to be defined simultaneously. This was defined for s greater than 0, and if we look at the intersection of those two sets, what do they have in common? Well, s has to be greater than 0 for both conditions to be met. So oftentimes we can find the Laplace transform of linear combinations by simply doing the Laplace transform of each individual piece. The next thing that we want to discuss, so if you go back through everything that we've done up to this point in 7.1, the directions were find the Laplace transform of a given function f of t, and we've been able to successfully find the Laplace transform for all of them. However, we said that sometimes, because of the nature of this improper integral, not all of these improper integrals are going to converge, and therefore not every function is going to have a Laplace transform. We would like to kind of know and have a criteria that would tell us that, okay, if I'm given a function, when will its Laplace transform exist? And to help us come up with our criteria, we have definition 7.12, which is the definition of exponential order. We say that a function f is of exponential order if there exist positive constants c and m greater than 0 and t greater than 0. So c is just a constant, it could be positive or negative, but m has to be greater than 0 and t has to be greater than 0, such that the absolute value of f of t is less than or equal to capital M times e to the ct power for all t greater than capital T. So this doesn't have to be an equality that holds for all real numbers. It just has to hold for sufficiently large t, meaning t greater than some prescribed capital T value. Okay. Some examples of functions that very easily meet this criteria would be things like polynomials. So any polynomial will always grow more slowly than any exponential. So polynomials would fit into this category, as well as like sine and cosine, etc. Also, the exponential functions themselves fall into this category. And what you're essentially seeing is that if you have something that's going to be lower than exponential, the exponential term is going to kind of dominate it very far out. So once you reach some point capital T, the exponential function will always be greater than the little function f of t. So for example, here we saw the ones that were kind of mentioned above. E to the t is greater than t, so t would be of exponential order. The function e to the negative t would be less than the exponential function itself, e to the t. So that means that e to the negative t is of exponential order. And likewise, 2 cosine t is also of exponential order because, for instance, it would be less than 2 e to the t. And then one of the things that we see that's not going to be of exponential order would be e to the t squared. So e to the t squared is not of exponential order. It would not be possible to find some capital T, some c, and some m greater than 0 such that this exponential term would ever be less than e to the t squared. So here's an example of one particular type of function that is not of exponential order. And this brings us to theorem 7.12. So a sufficient condition for existence is, let's suppose we have a function that is piecewise continuous on 0 to infinity. If it's also of exponential order, then its Laplace transform will exist for s greater than c. And that c, remember that c coming back up here, in the definition of exponential order, that c is the part that's going with the exponent of the exponential, e to the ct. So when s is greater than c, then that Laplace transform of that function will exist. So this is good. This gives us a sufficient condition to check to see whether or not a function's Laplace transform exists. Let's do an example. In example 6, we want to find the Laplace transform of the following piecewise continuous function. So let's find the Laplace transform of f of t, where f of t is equal to 0 when 0 is less than or equal to t is less than 3, and 2 when t is greater than or equal to 3. So this Laplace transform of f of t, this is equal to the limit as b approaches infinity, the integral from 0 to p, and actually let's not do that yet, sorry. You'll see why in a minute. This is the integral from 0 to infinity of e to the negative st f of t dt. But now because f of t is piecewise linear, we have the following things. Between 0 and 3, so this is going to be the integral from 0 to 3, e to the negative s of t. Over that interval, f of t is equal to 0 dt. And then plus, if we look at the integral then from 3 to infinity, that's going to be e to the negative st times f of t, which is going to be just 2 dt. For this first integral, this integrand is going to be 0, and therefore that whole integral will be 0. And so we're left with 2 times the integral from 3 to infinity of e to the negative s of t dt. Let's go ahead and work out this improper integral. This is the limit as b approaches infinity of 2 to the integral of 3 to b e to the negative s of t dt. Simple u substitution on this one. The limit as b approaches infinity, we're going to get negative 2 over s e to the negative st, evaluated from 3 to b. This is going to be the limit as b approaches infinity of negative 2 over s times e to the negative sb minus e to the negative 3s. As b approaches infinity, this term will approach 0. And so what we're going to be left with is negative 2 over s times negative e to the negative 3s. And this is going to be equal to 2e to the 3s over s. And I should say that this limit goes to 0. That's also provided that the s is greater than 0. So provided s is greater than 0. So there we have it. For this particular function that was piecewise continuous, its Laplace transform is 2e to the, drop my negative sign, negative 3s over s, and it's valid for when s is greater than 0. We'll finish section 7.1 with just one more observation. And this is going to talk about the end behavior of the Laplace transform. So recall that when we take the Laplace transform, the input is a function little f of t, and the Laplace transform spits us out a function of s, which we call capital F of s. If we want to determine the end behavior, so what happens to the Laplace transform f of s as s approaches infinity, well, the answer is if f has a Laplace transform, then the limit as s approaches infinity of f of s, this will be equal to 0.